So I hope you all had a nice cup of tea, and after some fundamentals I'll recap the highlights again to realize what we're doing, and then we start looking at how we can mix different fluids at the microscale. I put this slide in here again because you can't see it often enough how small the volumes are that we're actually working with. So if we work at the centimeter scale, we're typically working with milliliters to liters in terms of volumes. Whereas if we go to microfluidics, we are at the micrometer scale. I've got a bug that really likes the slides. And that means that we're working in femtoliters to picoliters, which means that the volumes are really small. It is important that we keep that in mind. On the first day I showed you the concentration of some of the biomolecules. You need to make sure that actually the volumes that you're working in, you've got sufficient copies of your analytical target still present within that volume. So they're bitey?
Sometimes, you
okay.
don't know.
I thought all the nasty insects and animals were only in Australia, and here it was completely safe and didn't need to be scared of snakes or anything. So yeah, I'm
Good friends.
we've got spiders this big at home.
Ah.
They are my friends because they eat mosquitoes. So we do biological warfare at home. I tolerate big spiders on the roof, particularly the big ones because they don't make cobwebs, so the house doesn't get dirty. But they eat all the mosquitoes and the flies. But they are, yeah, they've got big legs, and you can see the hairs. They've got big hairy legs. So we've got some impressive spiders at home. But wasps, bumblebees, we don't have a lot of wasps. In Europe there's a lot of wasps, but I'll be careful. This critter has been around in the lecture theatre. So if I hear any of you squeal, it will be that wasp. It was in here yesterday as well. Yeah. Unless it's a new one. So when we were just talking about the beauty of microfluidics, that we have laminar flow, and that means that we can selectively work on the difference in diffusion constants to separate different molecules. So we've got the distance that a molecule diffuses depends on its diffusion constant, which is a molecular property, as well as the time that you give it to diffuse. So diffusion constant says how fast it will go per second. You multiply it with the time and you end up with a distance. For an antibody, that's about 40 micron. For a small molecule, that's a lot larger. And then we saw that in 5 seconds, an antibody can move a lot less distance than a small molecule. And if we give a certain distance, it will take a longer time for an antibody to cross that distance, or for a protein, than it will do for a small molecule. We are working in the laminar flow regime, which means that we do not have all the turbulent flow swirly-whirlies around that you can see showing up in either when you see smoke being introduced into a particle-free air, or when you see water coming out of a garden hose, or when you look at a river. There's turbulent flow, there's all kinds of eddies going around. We are at the low Reynolds systems number. Typically in microfluidic systems, the Reynolds number is under 1, which is a lot smaller than being under 2000, which means that our flow is laminar. And here we can see an example of 2 blue dyes, or a green dye, a blue dye, and a red dye being introduced in a channel. They come together because we are in this laminar flow regime. They will just continue to nicely go along next to one another, and there's no mixing taking place. So what about mixing? The first thing that we could think about is just mixing by diffusion. So if we've got our 2 different reagents coming in, called A and B here, on the T junction, the flows come in, they meet each other, there's nowhere to go but down, so both flows just nicely form a contact line and they go down the middle. If we have a highly diffusive small molecule sitting in our liquid B and not in our liquid A, we can see that the compound from A slowly diffuses into the flow of B, which is illustrated here as the diffusion zone. And you can then wonder, how far down the channel do you need to go to have this area completely diffused? So have an equal distribution of our analyte that was present in B, have that homogeneously separated across the whole channel width. If we think about how that looks like in terms of an experiment, here we've got not a T but a Y intersection, just because it's always a little bit hard for flows to go around a right corner. So if you want to have pretty images, getting a Y shape instead of a T shape always makes the pictures nicer. So here we can see that we've got a Y-shaped channel of a certain width. We've got a fluorophore coming in that only fluoresces in presence of calcium. And we've got some calcium chloride here coming in at the other channel. We can see that at the point that these two mix, that the first little bit of calcium meets the fluoro 3 dye, we can see that fluorescence comes in. This is a large molecule. Calcium is a larger molecule than calcium. So calcium will be diffusing a lot faster into this channel. And here you can see the diffusion of calcium, which is a little bit helped at the interface. So we can see a little bit more diffusion.
If I don't come, please take lunch.
Yeah. So we have a little bit more fluidic effect at the edges. So we've got a little bit of deviation here. But you can see in the middle, we get an increasing amount of diffusion of our calcium into the dye. And we can see a growing amount of fluorescence being formed. Here we've got the XY and XZ view. So this is looking from the top. This is looking from the side. And you can see that the zone gets wider and wider by diffusion, but it takes some time. And you can also see that it gets wider because the image here is taken, what was this time point? At the different lines. So here at the beginning, we can see that we've got a relatively narrow diffusion line. The further we go down the channel, the wider that diffusive line gets. And that formed the basis of that mixing. Again, we've seen the capillary number on the Reynolds number. The Peclet number is a similar ratio, and in this Peclet number is looking at the mixing. And Peclet number looks at the convective forces over the diffusive forces, which is the product of, again, the linear flow velocity, the length scale of the flow, which is again this characteristic length, which is 4 times the surface area divided by the perimeter, so that the equations apply to round channels, oval channels, square channels, triangular channels. We can also always calculate the characteristic length independent of the geometry that we make, and the diffusion constant. In a microfluidic setup, it is best to think about microns. So if we're in a large system, 10 by 10 centimeter, and we calculate the Peclet number, we end up with a Peclet number that's really large, in the millions. If we do the same sums for a microchannel, we end up with a very small Peclet number, which is not surprisingly, because in microfluidics we are driven by diffusion, whereas in the large scale we're driven by convection. So the Peclet number gives you a little bit of an idea where you sit on the mixing based on convection and mixing based on diffusion timescale. Low Peclet numbers, your mixing will be close to non-existent, and you will have the laminar flow as we can see here in this image. We can use the Peclet number though to understand how long our channel has to be to, for mixing to be initiated. If we've got bovine serum albumin, which is a protein, it's got a diffusion constant of 70 square micron per second. If we pump that at a velocity of 50 micron per second through a microchannel, that is 100 by 100 micron. The Peclet number is 50 microns per second, multiplied by 100 micron as our characteristic length, divided by the diffusion constant is 71. This means that our characteristic time to mixing to start will be 142 seconds, and the length of our microchannel that we need for this mixing to take place is 7.1 millimeter. So we need a reasonably long channel for this to start mixing. So if we looked at the H filter in the previous lecture already, where we've got a solution coming in with some solutes and an acceptor phase coming to the other side. We can use the Peclet number as well to calculate how many of the particles would actually have ended up with our extracted fraction, or if we in this instance look at BSA, bovine serum albumin, if we're looking after doing an assay for a small molecule drug, where we don't want to have any interferences from protein. Maybe we want our conditions to set up in the way that all our protein stays in our donor and then goes to waste, whereas only our small molecule drugs are being extracted. So if we work in this system with, again, a flow velocity of 50 micrometers per second, our channel is 100 by 100 micron, there is very limited diffusion of protein, of the BSA, over a time of 7.1 millimeters or 142 seconds. Whereas for a small molecule, like our acetate, the diffusion constant is 1400, Peclet number 3.6. In 7.1 seconds, or after a distance of 350 microns, we actually get significant transport of our acetate into this other channel. So if our channel is between 357 and 7.1, 350 micron and 7 millimeters long, we can have a very good separation of our extracting our acetate out of the sample phase without significant diffusion of BSA, because we are under the typical time required for BSA to diffuse to cross across this line. So we can use the Peclet number to predict which compounds are going to be crossing through the H filter and which ones are not. Another interesting application of an H filter is to look at good swimmers. So if we look at sperm and we look at in vitro fertilization, one of the processing steps that is done in the clinics is to separate the highly motile sperm cells from the ones that are not highly motile, which is pretty much separate the good swimmers from the bad swimmers. You can use an H filter for that as well, or a similar setup. So in the picture here, we've got a sperm sample being introduced. And the sperm typically is in laminar flow and therefore will be following the flow lines and get out on the other side of the microchannel. If we've got our good swimmers though, they won't be sticking to the flow lines. They will find their own way, which means that the highly motile sperm will actually end up in the acceptor phase here, because it is not only the migration, the movement of the motile sperm is not only dictated by the flow that it's in, it can swim by itself. So even though it's within the laminar flow regime, the sperm that's highly motile will swim into the acceptor phase, whereas the sperm that's not very motile is getting moved with the laminar flow to the waste. This was done, I don't have a year here, I think somewhere in around 95, and the device got implemented in IVF clinics, and I then saw a presentation just before COVID, where the whole generation of the first microfluidic IVF babies was around 20 years old. So this is the use of the laminar flow in microfluidics has readily been commercialized and adopted in IVF, because it's a very easy, shear stress-free way of separating the highly motile sperm from the ones that are not very good swimmers. So the question for this lecture is, how can we mix? If we actually do want to mix, because I think a lot of the students here are doing nanoparticle, nanomaterial synthesis, a lot of you actually do like to mix, and laminar flow may be all well and good if you're a separation scientist, but you're interested in mixing. The ways that you can mix is using passive devices where the only energy that you use is from a pump, so you use fluidics, so you can do it through injections. You can make little droplets that are interdispersed in one another, and one of the funny things that if a droplet is in a channel, it actually rotates, so a droplet by itself is a very good mixer. You can put structures in place to cause chaotic mixtures, so you put obstacles in a channel that mimic the turbulent flow, and you can use lamination. So we've got a couple of different ways that are illustrated here. The picture here is the injection of substreams. So if you have two flows, it takes really long to divide. But if you have 6 times 2 flows together, the diffusion system's distance in each of those will be the same, but the flows are closer. So if you can split the flow in a lot of parallel flows, that actually allows you to realize mixing a lot better by laminating your different flows next to one another, which could be done parallel or sequentially. So here this is sequentially periodic injection. You can have zone A, zone B, zone A, zone B, and if they are alternating quick enough, you can get mixing happening by diffusion longitudinally. There are split and recombined mixtures where you've got 2 flows sitting next to each other, are being split and then recombined under another angle. And if you go from that way, we've got a very small contact area. If we then go that way, our contact area is a lot larger, so we can have more diffusion. Then we can rotate the flows around again, split and recombine. We can have little narrow areas again to reduce the distance and therefore the time that we need to have the fusion take place. We can use high energy collision to have very high flow rates and therefore locally increase that Reynolds number. So if you've got 2 flows really come into each other heads on, we can create some energy waves and get mixing happening that way. So they are the active tools that we've got to achieve mixing over the passive one. And then we've got a range of different active ways where we can actually do something with our chip using external sources. So we can create a little stir bar. For example, a magnetic stir bar that we put in a microfluidic cell. We put a magnet underneath, and we've got a little stir bar that is just as an impeller mixing. We can use pressure difference driven devices with valves or pumps. We can use magnets to move particles from A to B and drag liquid around and achieve mixing that way. We can use electric fields to mixing because we can selectively move analytes from one part to another. We can use dielectrophoresis, that we'll be talking a little bit more in detail this afternoon when we talk about the particle separations. We can use acoustic forces. Acoustic forces can also be used to move particles and move liquids around. And thermal processes increase the convection as well. The easiest way to get mixing to occur is just to change the channel length. What does channel length buy us? It buys us time. We work at a certain linear flow velocity. The longer our channel is, the longer it takes to get through this channel. We haven't done quite microfabrication yet, but there's our friend again. Hello, friend.
These are 4. 1, 2 are sitting here.
We're under attack.
They are sitting here. 2 are sitting here. 1 is there. 4.
Okay.
I think.
We started off with 1 yesterday, so let's see how we get through the day. Maybe we've got.
See 4 now. 2 are sitting silently here on the projector.
Okay, let's keep them there.
On my side.
Let's keep them stationary. So making a channel longer buys us time, but the problem is that we make these chips using microfabrication facilities. And typically the larger the chip, the more expensive it becomes and the harder the process. So large screens, large television screens are more expensive than smaller ones. Large chips, microfluidics chips are more expensive than shorter ones, which means that we typically go for a serpentine shape if we want to increase the channel length. Don't. So making a lot of curves means that you can have a lot of path length on a very small area. So if we have a channel that is still 100 by 100 micron and we want to pump the liquid through at about 0.1 microliters per minute for both the water and the sample that we want to mix it. Our length that we need for mixing is the velocity times the characteristic length over the diffusion, which equates the Becklet number times the characteristic length. So our velocity is 2 times the volumetric flow rate divided by our characteristic length, divided by our surface area, is in this instance our flow rate of 0.1 microliters per minute, comes down to 3.3 times 10 to the minus 4 meter per second. So we convert the linear, the volumetric flow rate into a velocity, into a linear flow rate. So we go from microliters per minute to meters per second. So we go from volume per time to distance per time. If we look at acetate, the characteristic length required for mixing acetate is 2.4 millimeters. The time to do that is 7.1 seconds. If we look at BSA, we need 50 millimeters to mix from one side to another. If we then say that our serpentine is on a square with half of it covered with a channel, then that's the area that the microchannels take, and then we can calculate how many of the zigzaggy turns we need. So this is one turn, this is the other turn. We can calculate what the length is and therefore how many turns we need to realize the channel length that we need to mixing to take place. And that will then be taking place in about 140 seconds. So if we've got a channel that's got 7 zigzaggy things going up and down, then in 140 seconds we will have BSA being mixed in our channel. So for mixing acetate, we need a short channel and a short length. If we make this channel a lot longer by having 7.5 turns, it takes 140 seconds from going from this intersection here to the outlet and will be mixed there. So the other option than adding turns and turns is to do parallel lamination. So to have, instead of having one interface, you can have multiple interface. Where was my 47? So if you can calculate from that perspective, if you want to mix in a certain time, how many layers you want to have. So, did I do the calculations here? I did this last night. So if you've got n different layers, then the time that you need, so number of different slices sandwiched, then you need 1 over n less time. So if you've got 1 layer, then you've got 1 amount of time.
Why we increase the channel length in zigzag motion, not in linear motion? In linear?
You can do either. So this is adding it laminar channels in the length of the channel. You can also chop them in space that way, but that needs a higher level of fluidic control. So it is lamination lengthwise you can easily control using your fluidic structure. If you want to do segmented flow one after another, you need to have pumps that very quickly pulse and that is not easy to solve using your fluidic structures. So you're absolutely right that lamination sandwiching in can be done both perpendicular to the channel and in flow. The splitting it up in different sections is easier done with using the fluidic structures if you go lengthwise, but the sums will be exactly the same, other than your interface will be determined by your channel geometry, so your calculations will slightly change. But you can do both. It just depends on how good your switching of your pumps and valves is. So it becomes a control systems engineering problem if you want to do it sequential, and if you want to do it linear, it becomes a fluidic design solution. Both will be having exactly the same outcome. It is just whatever engineer you talk with is who's going to. So either you're going to have simple chip, complex pump control, or a complex chip and simple fluidic control. So it's a choice to make. There is not really a right or wrong in it, but yeah, that's a very good point. So if we've got one layer, then our time is 1. If we double, then we can halve our time, and so on and so on. So we can calculate that if we want to have the separation happening in 3 seconds, then we need about 7 layers sitting next to each other in our device, and that way we can achieve the mixing in a lot shorter time. Here we've got the parallel and the sequential lamination in another picture, where the split and recombine allows for very efficient. So in the first stage, this is the structure that it looks like, and you can see it's 3-dimensional, because here a part of this channel is splitting up vertically, then being put on its side before it's being merged back again. So we've got the channels, 2 channels come in, they are split vertically, rotated around and being folded back together. So at the first stage of the split and recombine mixture, we've got our dye coming in with our solution, and we've got one single interface as we just spoke about. After having gone through one of these mixing units, the flow gets halved, so we've got a wasp. We've got 2 different flows now that are both half the height of having a dye and an empty face sitting next to each other. If these then, by having the channels geometry being put on its side, and again laminar flow allows us to do that, we can put these 2 on the side, and we can see that at this stage we have 1, 2, 3, 4 interfaces where the fusion can take place for the mixing. We can then go through another operator, so we chop this one in 2 different layers. Here we've got dye, no dye, dye, no dye. On the top half, we also have got dye, no dye, dye, no dye on the bottom. We can then put them up straight and put them back together. And now we have 1, 2, 3, 4, 5, 6, 7, 8 different interfaces where our mixing can take place. So you can see that with the sequential lamination, where we get all the flows taking place, we can get very efficient mixing taking place. So the mixing can be done across the 3 dimensions. Then we have also a range of features if we want to do mixing to kind of try to mimic the turbulent flow profiles using fluidic structures. And that is pretty much just pestering the flow. So we've got our solute and our solvent coming in. And you can see here that there is no easy straight flow path anymore, but the liquid has to go around the corner and then a sharp corner again, and it hits a wall again. And that creates little eddies, little swirly whirlies at the corner. And it's those swirly whirlies that then allow you, even though you are still under laminar flow conditions, to have convective mixing, because you get little flow areas at each of these corners that will get the mixing to take place. Another way to achieve that is just to put a lot of pillars in place, or a porous material, because then again it's not as controlled as a split and recombine mixture. But these pillars here will create both. It will split the flow and recombine, because the flow will have to go around the pillars. And that way you increase the surface area where your solute and your solvent are forced in contact, and you will be able to get mixes taking place. And here we have a channel that just goes into a lot of different directions, again relying on the fact that we get differences in flow velocity between the long and the short corner, causing these circulatory flows at each of the angles, and they start working like little stir bars to get mixing to take place. So this one is more efficient than this one, but if you get your channel to do weird enough zigzags, you can enhance the mixing compared to a diffusion-only different process as well. If we go to intermediate Reynolds numbers, you can see that the things people have come up with are increasingly complex. So here there's droplet-like features where part of the flow needs to go back in each of the mixing stages. Here we've got the flow, it goes up, left, down. So again, we rely on all these eddies at the corners. This one, they're all variations of the same theme, and typically these designs arise from computational fluid dynamics. So there is software packages like ANSYS and Console, and there you can put some obstacles in and see what your flow lines do. And if you can see that your flow lines get large eddies, large circulatory parts, that is where you can get good mixers. So a lot of these designs were thought like what's happened there. Then the length and the width have been optimized using thermodynamics, fluid dynamics, and then you can see if you can make the devices and evaluate the quality of the mixing. This is one of my favorites because they're relatively easy to make. It is putting some traffic humps on place. So you only need to put some lines, well, if you put some little angled features on the bottom, it is very much like driving your car across a traffic hump. Everything in the car moves, particularly when you walk too fast. So if you've got a high flow, you've got laminar flow happening, but you put a traffic hump on the middle of your channel, everything will have to move up, compress and mix, and that creates a lot of diffusion. So these are referred to as the herringbone mixer, where you get a change of flow because the flow hits an obstacle and it will start getting a circulatory motion happening in place, which is what you see happening here. So you can see here the traffic humps are not only straight, they've got a straight corner. And that is to try to redirect the flow and then go up the wall and try to get a circulatory motion. Here from the inlet we can see the die and our buffer coming in. You can see little effect at the first one, at the short end, because it doesn't quite redirect the flow yet. But here we can see that the traffic humps actually get a flow happening during the surface, and you can see that the mixing, the change of that flow pushes the die further to the center of the channel. Then they go the other direction again, but the flow still pushes this further and further. And you can see that every time that we go from a short arm to a long arm, we get more of that rotationary flow being happening. And that means that our mixing here, if you look at this distance, our mixing is a lot more efficient than it was when we would just have had laminar flow here. Because here you can see on this distance really nothing has happened yet. So we would have still have no mixing at all without the features. But with these herringbone structures on the place, we actually can get a different flow motion that promotes the mixing between our solvent and our solute. So they are a couple of different ways to work with fluidic structures, with fluidic design. There are also ways that we can actively mix using pumps and valves, where if we get a pulse of solvent and a pulse of our analyte to come together into a microchannel, we get that segmentation happening sequentially. And we can mix that way because our diffusion, if the droplets, the segments are small enough, we can anticipate that mixing will be working that way. We can achieve the same thing when we've got our solute and our solvent coming in, but we apply little teasing pulses using a pump from the side, where we just push the liquid to one side of the channel and then to the other. Again, pretty much getting the idea of a gyro rocker, but then organized within the microchannel. This in here is the little stir bar, so if you've got a magnetic element, you put a magnet underneath, you can get mixing to take place that way. You can use the electroosmotic flow and then have an AC voltage. If you have changed your polarity, your electroosmotic flow goes the other direction. So here we've got electroosmotic flow pushing one way, pushing the other way, achieving mixing that way. And here we've got, again, AC voltages to create pressure waves in one direction, causing pressure disturbances. So if we all of a sudden have a large expansion of our channel, we get change in pressure because the pressure is divided by the channel width. If we all of a sudden have an expansion, we get a pressure drop, which again results in these eddies, the recirculatory flows, which pushes your liquid out and in and enhances that mixing. Electrokinetic fields, and the last one here was using temperature. So if you use the temperature of one of your solutes and not the other, you change the viscosities, and you can use your change in viscosity there to affect the mixing. Sound waves are very good. We're working at a small scale, and small particles can be moved by sound. You realize that if there's a festival, or even if you get close to the speaker of your mobile phone, sound is a physical vibration. And the force of this vibration is enough to enact movements inside the microchannels. So if we've got a PDMS microchannel here with a piezo transducer, which is not much more than the little membrane. I'm not sure if you've ever dismantled a little speaker, but there's a little vibrating thing in a portable speaker as well as in your phone. So that's the piezo transducer that's sitting here. If you have a little bubble sitting in one of these cavities and you start applying some sound waves, which could be the acoustic waves, so it could be just sound, you get little vortices happening at this bubble because the transmission of the sound through the gas bubble is different to that in the material, which means that the bubbles are sitting here all at the corners, and we'll learn later PDMS is a hydrophobic material, so bubbles really love to stick to PDMS. So in this device, little bubbles are sitting here at all the cavities, and each of these bubbles at these tips creates a little eddy once the sound is switched on. And again, those eddies will allow you to mixing. So using a sound field, using an acoustic wave, you can mix reagents by creating these force fields. Light can help in inducing heat, or no, in this case this was particles. So here we've got two different oil phase and a water phase which has a photosensitive material in there. If we apply the pulse of light, it means that this photosensitive aqueous phase becomes a particle. This particle will start bouncing around based on the pressure differences in the cavities, and there with that start dragging the other liquid around. So they become pretty much helpers and little stir bars because of these expansion and contraction areas. So if we've got our two oil phases separated by the thin film of photosensitive dye without any light being applied, everything is liquid, we have laminar flow and not much happens. We'll have a little bit of disturbance, but the geometries here are selected that we don't get too much mixing. However, if we polymerize this into little beads, the beads will start following the flow lines a lot better. And you can see here that these beads start taking the circulatory flow patterns that are happening, and you get a high level of mixing coming out. So you can have your flows going continuously. Nothing happens if your photoactive compound is still a liquid. If you make little particles here from your phase, then these droplets, these particles will start making the mixing. Another way of doing mixing is that people create cilia. How many biologists do we have here? From biologists. So what are cilia?
Not biologists, but understand.
Yeah, so what are cilia?
These are the small hairline structures outside the body of amoeba or paramecium. These are single cell organisms.
Yeah, so they're single cell organism, but there's also cilia in our lungs. So our lungs are covered by a mucus layer, but we don't want our lungs to be full of slime and liquid, because then we can't have air transport anymore. This is getting interesting. So the surfaces of our airways are coated, have little cilia in there. And they are little pillar-like structures that continuously pump the slime and mucus back up. So our lungs like to have a clean layer of mucus in there, but there's the cilia that are moving, pumping the slime back up so that we can swallow it and get it into our intestines, and our lungs get continuously refreshed. So a lot of biological systems have these wavy structures on the surface to transport viscous liquids. Some very clever people thought that we could use that in microfluidics as well. So they started making little pillars, introducing some of them a small magnet on the top. And then you can, using an external, so if you've got a magnetic tip on a microfabricated cilia, and you move a magnet underneath, you can get the cilia to do the same movement as that the cilia in our body do to move the liquids up. So here we've got a microfluidic device here with a column here of these cilia. Here you can see them on an SEM in PDMS, so they're just a little circular pillar, and the tip of that pillar contained a little magnet. By actuating these cilia, you can get from a non-mixed condition to a properly mixed condition by just having them move up and down. So here you can see the way that it works. So there's magnetic, 4 different electromagnets. If you get the fields, you get the cilia to move one direction, and you can get them to flop in the other direction. Another way of getting cilia to work is using light. So if you make the cilia not out of one polymer, but out of 2 different polymers, you can get, depending on the light, you can get the polymer to either stand straight up or like a bimetal move around. If you make the cilia like a bimetal, where the materials respond differently to an electric field, you can apply a potential difference and you get the cilia to either stand up or fall back down and get them to move that way. The last way of realizing actuation is making them kind of inflatable. So if your cilia are hollow tubes and when they're and you apply a pressure difference, you can actually, by pneumatic pressure, get them to curve around with the flow. If they're not actuated, because they go with the flow, if you apply pressure, they become a lot stiffer and you get to get them to stand up. So you can pneumatically get your cilia to either stand up or go with the flow. And by actuating that between the standing up and the being folded over, you can get them to move and help as a mixer. So there's a whole big toolbox of how you can get different parts to mix. And if you design that, a device, there are a couple of different decisions that you can make, and as we've already seen with the sequential mixing or the parallel, there is not really a right or wrong. There's just a large toolbox, and some applications, some solutions will be better to some applications. So the big choices that we have is that we've got active mixers where we need an external force, which could be a magnetic field, it could be sound, it could be an electric field, it could be the actuation of the cilia. But in active mixing, we have something that we need to control to get the movement in motion. Before that, we talked about the passive mixing systems, where we use the fluidic design to enhance the mixing, which could be either by increasing the amount of surface area and therefore decreasing the diffusion time required for full mixing. That's your split and recombine mixing. Or you create expansion contraption channels where you create eddies on the surfaces and get your liquids to have more circulatory flow and therefore mix better that way. Or we have the structures implemented on the bottom, like the herringbone mixer, that instead of having laminar flow, we start getting the flow to kind of go around in the channel. That way enhancing mixing. So the choice is very much, typically the active mixers are a lot more faster than the passive mixer, but it complicates your instrument design. So it depends on your application need, if you need to achieve mixing, if you're happy to just get to a serpentine channel and increase length, if you want to get a passive mixer by using some design elements, or if you want to go for an active mixer, make your instrument a little bit more compact, but still know that you've got a simple chip and very fast mixing. So there is no good or bad, but this provides a little bit of an overview on how you can realize mixing in the microchannels. Which brings us to lunch, if there's no further questions. So yeah, some of the mornings, so I think some of the days we have a 2-hour lecture in this block and some of the days it's a 1 hour. So we're finished a little bit earlier than the other days, but I think we can just take a little bit of a longer lunch break. Any questions?
It seems quite complicated when it works. Come to a practical.
It is very much a toolbox.
Yeah.
So there is a couple of different problems, there's a couple of different solutions. The same thing as
Exactly.
we'll see this afternoon as with the particle separations.